This is the first of two videos on the topic of inverse functions. There's a lot to talk about, so we'll go ahead and get started right away. So, what is an inverse function? We had thought of functions in terms of it being sort of like a machine, where we put one number into the machine and another number comes out. And we might ask ourselves the question, well, what if we want our original number back? How can we get that? And so what we have to do is we have to build another machine that takes the result and converts it back. And this second machine is called an inverse function. And so that's what an inverse function does. It reverses the process. When we change a number, it reverses the process and brings that number back. So let's see what that looks like more concretely. Here is a function, and if we put 3 into that function, we get 2 out. And what if we want our 3 back? What we have to do is create a new function. So we put our 2 into this new function, and 3 comes back. Now, for this to truly be an inverse function, I should be able to put any number in here and get the original number back. So I don't have to keep changing and creating new different inverse functions. There has to be just one function that does it. So how do we know that this wasn't just lucky, like it just worked for 3s and 2s? How do we know? So what we have to do is we have to go back to our discussion about composite functions. Instead of dealing with numbers, why don't we just put this first function directly into the second function? So that's what we've done here. We put the first function into the second function, and we've simplified, and we get x. And so what this means is if we put x into our composite function, then we get x out. So x came in, x came out, so we got what we started with. So those two are composite inverse functions. But not quite. We have to actually make sure, we actually have to check that the reverse process also works. So being able to take this function and put it into the first original function. And so algebraically I have done that, and we simplify and we get x. So because it works both directions, both composite functions work, they both give us x, the original, then those two functions we have proven that they are inverse functions of each other. Now the notation for inverse functions can get pretty awkward. So despite even with my scribble, which makes it even worse. So if we put the inverse function inside of the original function, or if we put the original function inside the inverse function, either way, if we get x, then those two functions are inverses. Now, the notation that was used there is pretty unfortunate, because actually we've seen this notation before, but it actually meant a very different thing. So we know that this is the notation for a reciprocal function. So if this was x to the negative 2 power, it would be 1 over x to the positive 2 power. And so the reciprocal function and the inverse function, two very different things, but the two notations are very similar. Here we have the inverse function, so the function inverse, and then over here we have the function reciprocal. So this is saying take the negative 1 power of this function. This is trying to say this is the inverse of this function. So it's very confusing. It's very unfortunate. Sorry about that. I didn't invent it, but this is the way it works. So we're going to just have to be careful with our notation. Okay, so here in our book, we should already be familiar with a lot of inverses. So like if I take x and I add 3 and subtract 3, we get x. So adding and subtracting are inverses, multiplying, dividing, square root and square rooting, squaring and square rooting. They're all inverses. And in fact, there are some others that you should know. So we have anything like, a cube and a cube root, or an n power and the nth root are inverses. We'll take a look soon at exponents and logarithms. They're inverses, sine, inverse sine. We'll get to those later on as well. So these are all examples of inverses. Okay, so you might have asked or thought to yourself, well, this function was given as the inverse of this function, but how would I actually find this inverse function algebraically? And so I'll go ahead and show you this process here. So what I would like you to do in order to find the inverse of a function is, if it's given to you in this notation, go ahead and change it into y. And then what we want to do is we want to switch x and y. We just change that into an x, change that into a y, everything else is the same. Then we want to solve for y. Okay, so we're going to add 4 to both sides. I did 2 steps here at the same time. I've just moved y to the third on the other side. So we get this, and then we go ahead and find the cube root. And then since it was originally given to us in f of x, then we use this notation. So now the inverse function is this. And so that's how you find the inverse function algebraically. You just switch the two variables and then solve. Okay, so why don't you try an activity right now where you go ahead and try to find the inverse of this function. In this function, if you give me Celsius, I'll tell you what the Fahrenheit is. But not everyone works in the same units here. So let's make a function where we want, if you give me Fahrenheit, then I'll give you Celsius. Take a second to do that. Okay, so you should have come up with this function, right? Where here we take Celsius, we change into Fahrenheit. Now we're putting Fahrenheit right back into a function and getting Celsius back. These are inverse functions of each other. Okay, so that's the algebraic process. But now let's think about geometrically. What does it look like graphically? And so I have the graph of the functions that we've been talking about. Here in green, here in red is the 1/3 x plus 1 function, and then the green function is the 3x minus 3 function. These two are inverses of each other, and I've added this third line here, y equals x. And hopefully you can see that if this were a mirror, then these two would be mirror images of each other. Or if I were to pick this and flip it over the y equals x line, it would become the this other function. So, but maybe that was just a curious case of this of just those two functions. Does it always work that way? Let's take a look at another example. Here in this example, I have in red, I have the cubic function y equals x cubed. It looks like this. And if I were to follow the algebraic process of finding the inverse, we get x is equal to, it's the cube, x to the 1/3 or the cube root of x. And so that function is here in green. Again, with the y equals x line, we can see that one is the mirror image of the other, one is the flip of the other one over the y equals x line. So actually, it turns out it always works that way. That's one of these properties of the inverse functions. And there's some conclusions that we need to make. One of them right away, we need to see that the domain of one function becomes the range of the other function. Okay, so the domain and the range flip. Let's see what that looks like. So if I take a look at this first function here, if I take a look at the point, actually this one might be better. If I look at I'm sorry. So if I find a point here, like that's 3 and then 2. Okay, so on the red line I go 3, 2. The corresponding, if I were to flip it over, it would be 2, 3. Since the 2 and the 3, they change places, the x and the y's change places, and that's all the way down the line. If I go to 6, 3, then and I flip it over, then I go to 3, 6, and that gives me my new point. And so when you switch the x and y like that, that means the domain and the range are flipped as well. So So that's going to be the end of this first video on inverse functions. Be sure to check out the next video.